latest community session for the computer vision group. Today we have Dr. Ravi Mangal with us here on the call. He's a postdoc researcher at Carnegie Mellon University, and recently he started a new position at the Colorado State University as an assistant professor at the Department of Computer Science. In general, he loves to do research on safety and trustworthiness of automated systems. And that's basically what he's going to be talking with us about today, specifically about how to analyze deep learning systems using probabilistic methods in order to ensure that they are safe and understandable. So without further ado, I know I have not done him enough justice, but without further ado, I think let's give the good doctor the ground. Yeah. So that's it for me.
Thank you, Benedict.
Yeah.
So let me share my screen. All right. So thank you so much for having me here today. And I'm excited to be presenting some work that we did last year. So I know this is the computer vision group, but I'm not going to be talking about developing new computer vision systems. As Benedict mentioned, my interest is in analyzing systems. So this talk will be about analyzing vision-based autonomous systems. And I use a case study to ground what I'm describing. And yes, I'm currently at CMU, and I'll be moving to Colorado State in August. So the work I'm presenting has been done with some excellent collaborators, namely Corina Pasarianu, Divya Gopinath, Sinem Ketir Yaman, Callum Emery, Radu Kalinescu, and Wafeng Yu. And the particular work I'm presenting appeared as a paper last year in a conference called Computer-Aided Verification. So let's get started. So I first want to sort of describe and set the ground for what I mean by vision-based autonomous systems. So basically, I'm thinking about modern cyber-physical systems. Well, by the way, please feel, I don't know how these sort of interactions go, but please feel to ask questions. And I'm happy to take questions during the talk. All right, so I want to talk about cyber-physical systems. So these are basically systems these are reactive systems, and I'll say in a moment what are reactive systems, but these are reactive systems that combine software and physical components. So reactive systems are systems that are continuously interacting with the environment. So you can think that the system, say, perceives the environment, it takes some action based on the perceived state of the environment. This action in turn updates the state of the system as well as the environment potentially, and then we loop back to the perception stage. So this is like a typical reactive system. And in particular for this talk, we're thinking about reactive systems which use neural networks for perception and or control. So these are what I refer to as modern cyber-physical systems, the ones that are using neural networks for perception and or control. And these kinds of systems are particularly complex because they tend to use vision-based perception. And this requires processing high-dimensional inputs in the form of images, which in turn requires complex TNNs with millions or even billions of parameters these days. And to the right, you can see some examples of the kinds of systems I'm thinking about. So an autonomous car, there are companies trying to develop self-driving planes, or self-flying planes rather, robots of various kinds. So these are the kinds of systems that you should keep in mind. And sort of an important thing is these systems are intended to operate in complex environments, and they are often operating in safety critical settings. So we have to think carefully about whether these systems are safe. And in fact, as we know, autonomous cyber-physical systems can fail. I'm sure you must all have seen these kinds of headlines where various self-driving systems, cars in particular, have been responsible for horrific crashes that have involved loss of human life. So this is just to say that it's really important before we deploy these kinds of systems in the world that we have some assurance that these systems are going to behave safely and correctly. So the question then is, how do we do this kind of assurance, right? What does that even look like? And that's a complex question, and I'm not going to give a full answer in this talk, but hopefully I'll give you some hints of how this works. So we are going to use something called formal methods. So I come from a background of formal methods. These are a class of computer science techniques used to analyze systems. And here we have a simple sort of cartoon figure of what the general methodology is. Okay, so the box, you can think of it as uh, sort of where the formal methods live, but the formal methods, they basically take three inputs. Okay, so they need a mathematical or some kind of a model of the system as an input. Okay, it could even be a program that describes the system. um, you also need to have something called a specification, so that is describing how your system ought to behave, and this specification is usually some kind of a logical statement. Okay, and the third ingredient is again a mathematical model of the environment in which the system is operating. So given these three pieces, basically you can use formal methods to answer the question, does the system in composition with its environment, so the two parallel lines denote composition here. So does the system in composition with its environment satisfy my specification phi? Okay, so that's basically the formal methods. Like that's what we want to answer using formal methods. And I've shown here like some kinds of tools, some like classes of tools that formal methods typically tend to use. It's okay if you haven't heard of these things, but if you have, like basically you're thinking of tools like SAT solvers, SMT solvers, model checkers, theorem provers, and so on. Okay, and basically the result of this kind of a like asking this question using formal methods tools is either we get a proof, like an actual formal mathematical proof that my system along with the environment does satisfy my specification, or we get what is called a counterexample. This is some kind of an error trace that demonstrates how and when the system can fail. Okay, so this is the gold standard of formal methods. And again, we are not going to completely get to this gold standard, but we'll make some progress. Okay, so having set this up, basically applying these kinds of formal methods to autonomous systems is really hard. It's harder than doing this for traditional software, where formal methods have found a lot of success. So why is this hard? Well, the first thing is neural networks. Well, autonomous systems, as I just said, are going to typically have neural networks for perception and or control. And the perception could be vision-based perception. And these neural networks are super complex and opaque. So we don't understand what algorithms they're implementing. We know what low-level operations are going on, but we don't know sort of at a high level algorithmically what sort of what is the reasoning that's being performed by the neural network. Okay, so that makes it really hard. A second big challenge is neural networks do not come with logical specifications. So we saw on the previous slide that we need these specs for formal methods, for formal analysis, but neural networks don't come with specifications. Typically, the only specification that we have is the data, right? The data says how the network should behave, but beyond that, we don't have some logical characterization of the required behavior. A third challenge is the kinds of autonomous systems that we are interested in are intended to operate in very complex environments. So again, sort of think of a self-driving car, for instance, and that's an environment that's hard to model mathematically. Like that's a hard task. We might typically not even have a good mathematical model of the environment. And a fourth challenge is even if you could model the environment mathematically, you could come up with some logical specifications. Because these new modern autonomous systems are complex, formal methods do not scale. They are not computationally efficient to be applied to these complex systems. And in fact, this often tends to be one of the challenges of applying formal methods. They computationally they can be expensive unless you are careful about using these methods and developing abstractions that make them scale. So that's also a challenge. So we're going to see how we might get around some of these challenges. Okay. So for the rest of the talk, we are going to use a case study. So I'll be describing the ideas using a system called TaxiNet. Okay. So the construction and analysis of this TaxiNet system was a project between NASA and Boeing, and many researchers at UC Berkeley were involved in this. And this is intended as a case study that can help develop insights for the analysis of more complicated systems in the future. Okay. So what is TaxiNet? It is an autonomous aircraft taxiing system. Okay. So the goal of the system is to ensure that the aircraft tracks the center line on a taxiway. Um, and the system uses a neural network to get pictures of the taxiway as input, and then the neural network estimates the plane's position or state on the with respect to the center line. Okay, so you can see, for instance, the kinds of pictures that the neural network is going to get as input. Um, and for each input, the neural network actually returns two numerical outputs. So these are called the cross-track error, which is the distance of the plane from the center line, and the heading error, which is the angle that the plane's body makes with respect to the center line. Okay, so that gives us the state of the plane with respect to the center line. And then the system has a handwritten controller. So the controller is going to take this estimated system state produced by the neural network, and the output of the controller is going to be a steering angle that says how should the plane be steered next, okay, so that it keeps tracking the center line. So this is the basic system. Okay. Um, for the purpose of analyzing the system, we are actually going to make it simpler. So the system I described had continuous dynamics and a continuous state space, but we are going to make it discrete. So we are going to discretize this, make the state space of the system discrete, which means that the controller is also going to be discrete, and we're going to assume a discrete model of the airplane's dynamics. Okay, so everything we are going to make discrete. In reality, things are continuous, but for the purpose of analysis, we're going to make things discrete. And the numbers that you see at the bottom are just telling you how we discretize this system. So for instance, the CTE values, they range from -8 meters to 8 meters. And I'm going to describe what this -8 and 8 is precisely. But the CTE values range from -8 to 8 meters. But when we discretize it, we sort of discretize it into 5 discrete values. And the ranges are telling you what discrete value is assigned to what range of continuous values. The same thing with the HE values. Okay, so basically the point here is we are discretizing the system. Okay, so once we have this kind of a discretization, now we are ready to start analyzing this system. So the first thing that we need to do before we turn our formal methods crank is we actually need to have a specification of what is the kind of behavior that we want the system to exhibit, right? So if you remember the cartoon image that I showed, one of the ingredients is the specification. So a point that I want to convey on this slide is, although I had said previously that providing a specification for a neural network is really hard, and that's true, often it's easier to provide a specification when you consider the system as a whole. Okay, so here our system is the TaxiNet system. We're not trying to provide a specification just for the neural network that's doing perception, but we're going to provide a specification for the whole system. And the specification that we provide here, basically, what we want to ensure is, starting from some fixed initial state, we want to ensure that the system is going to perform safely on a straight segment of the taxiway for a finite number of steps. Okay, so we are being not super ambitious in what is our notion of safety. All that we are saying is, assume that the system or the airplane starts from some fixed state on the runway, and we want to ensure that it continues performing safely on some straight segment of the runway or taxiway for some finite number of steps. Okay, and the way we define safe here is to say that the plane should not go off the taxiway, meaning the CTE value, which was the distance of the plane from the center line, should be less than or equal to 8 meters. Okay, and this 8 meters comes from the fact that the taxiway is, say, 16 meters wide, and this was like a number given to us by our collaborators from Boeing. So the plane at the most should be between the range -8 to 8 meters. Okay, and the other constraint is the HE value, which is the heading error. should be between minus 35 to 35 degrees. This is saying that the plane should continue pointing sufficiently forward. You don't want the plane to be, say, pointing very much towards the left edge of the runway or the right edge of the runway. Okay. That's what this HE constraint says. And we can basically, given this kind of a specification, we can formalize it using some kind of a logic. So you don't need to know what this PCTL logic is. It's something called a probabilistic temporal logic. But sort of intuitively, we have two specifications that we can write down from what I described. So the first specification says, and again, you don't need to know the notation here. I'm going to say what it means intuitively. So the first specification says that the probability that the plane goes off the runway should be bounded. Okay, so it should be a very small probability. So we're not going to be able to give absolute guarantee that the plane is never going to go off the runway, but we are going to aim for a probabilistic guarantee that this event is very unlikely to happen. Okay, that's our property one. And property two is again saying that the probability that the plane turns more than a certain degree, which is this 35-degree limit, should be bounded. Okay. All right. So that's our specification, and I'll just briefly stop here to check if there are any questions before I move on. Okay, let's continue then. So now we have our specification, and now we get into the heart of the problem, which is how do we go about doing a formal analysis of the system. I had mentioned that this is complex because the neural network is complex, the environment is hard to model. So how can we get around these kinds of issues? So before we start thinking about it, let's again take a high-level view of what this taxonet system looks like. Okay, what are its components? So here we have four components that describe the system. Okay, so the perception DNN, and this is the neural network. As I said previously, it gets images from the camera, which is mounted on a wing of the airplane. Okay, and the neural network estimates the state of the airplane. So it produces what I describe right here as est. And this is the estimated value for CTE and HE. And we assume discrete values because we have discretized the system. Given these estimates, they are consumed by the controller, and the controller outputs an action. Okay, so this is now an action, which is how left or right should the plane turn in the next time step. And again, we discretize this. Okay. Given this action, the airplane's state is going to get updated. Okay, and the state gets updated based on or dictated by the dynamics of the airplane. So this is, think of these as just physics equations that describe how the airplane moves essentially. So if you once the controller says that the airplane should turn a certain number of degrees to the left or the right, we can plug these inputs into some equations, and that will tell us exactly what the next state of the airplane is going to be. Okay, and again, the state, remember, is just the position of the airplane with respect to the center line. And then the final piece of the system is this cloud, which is labeled here as the camera and the environment and the camera dynamics. So basically, think of this as the camera, and it basically, the camera captures the state of the aircraft and the surrounding environment and generates an image. Right, so it takes in the state of the aircraft and surrounding environment, generates an image, which then gets fed back to the perception DNN. So I would like to note that this blob, camera blob, and the environment blob that we describe here is actually super complex. So what kinds of processes are going on here? Well, the process of generating a digital image from the state of the aircraft is complex because it depends on the state of the environment, for instance. What kinds of lighting conditions are there? What is the weather? The time of day? Okay, it includes the complex physical process of generating a 2D picture based on a 3D scene and light sources. Okay, it also includes the dynamics of the camera itself. So the camera has something going on inside. When once photons are incident on the lens of the camera, there is some processing going on inside the camera before the digital image gets generated. Okay, so if you wanted to faithfully model this environment and camera dynamics sort of blob, we would need to model all of these very complex processes, and that's not going to be feasible. We are not going to be able to model all of these things. Okay, um, so um, so again, like, we want to analyze the system. We have a specification, but analyzing the system is challenging. One, because the perception DNN itself is very large and complex. Okay, and second, we don't have mathematical models of the environment and camera, or even if we do, these models are very complex. So that's our key challenge. Okay, and I should note that there is a lot of work on trying to address this kind of a question, like basically analyzing these systems and safety of such systems. But a lot of the past work has considered either simpler settings where you don't have vision-based perception, but you're using some simpler sensor, let's say LiDAR, uh, or these past works have tended to try to find counterexamples, ways in which the system can misbehave rather than try and find proofs of correctness. So we are going to aim for proofs in this talk. Okay, so how do we do this? Okay, so we have I've been teasing you how do we do this. So now I'm finally going to get to the point. So in hindsight, it turns out that we can apply a very simple idea to analyze a system. So note that the top two components of the system, if you consider the combined effect is to take in the actual state of the system S and produce an estimated state of the system SS. Okay, in essence, the top two components can be seen as basically doing state estimation. Okay, and we're going to leverage this observation. So the idea is to replace the top two components by a probabilistic abstraction or a probabilistic map that we call alpha, that goes from the actual states of the system to a distribution over the estimated states of the system. Okay, so essentially, this map gives the probability that the state estimated by the DNN is SS when the actual state of the system is S. And on the next slide, I'm going to tell you how we construct this map. But we are going to basically try and build this probabilistic abstraction. Okay. Why does this map need to be probabilistic? Well, there are two reasons. First, our environment itself is stochastic or probabilistic, which implies that each actual state of the airplane can map to a distribution over images that encode the same airplane state, right? Depending on the weather, the lighting conditions, the same airplane state can lead to a whole bunch of different kinds of images. So that's the first reason. And the second reason is our neural network is imperfect. So it's always going to make some mistakes. It cannot perfectly recover the underlying state, and it performs differently in different parts of the distribution. So that's why this map needs to be probabilistic. So let's see how we build this map. Basically, we can view this map as defining probabilistic transitions from every discrete actual system state to every discrete estimated system state. And the question is, how do we estimate these transition probabilities? Because we don't know them. Nobody has given them to us. Okay. And the key insight, and really the simple insight, is we can leverage confusion matrices calculated for the perception DNN to estimate these probabilities. So confusion matrices are a standard way of measuring the performance of classifiers. Just as a reminder, each row of the matrix represents the instances in an actual class, and each column represents instances in a predicted class. So for example, this confusion matrix on the right-hand side for HE, the rows here are, again, the actual, if we take, say, we look at a particular cell, so row 0, column 1, what it says is there are, out of all the samples in our data set, which is 11,108 samples, there are 2139 samples whose ground truth label is 0, but the classifier predicted as 1. Okay, so that's what the confusion matrix is telling us. And Basically, we can use this confusion matrix to calculate the probabilities that we're interested in. So here we have an example of the calculation that we can perform. So for instance, if we want to estimate the probability that the classifier is going to output label 1 for HE when the ground truth label is 0, the way we can do this is we take the entry in row 0 column 1 as the numerator, okay, and we take the entries in row 0, sum together the entries in row 0 in the denominator, and this then tells us the probability of the classifier saying HE is going to be 1, or the estimated value of HE is 1 when the ground truth HE is 0. So we can do this calculation for all pairs of HE estimate and HE, and similarly CTE estimate and CTE, and that will allow us to build this probabilistic abstraction that I talked about. Okay. So now once we build this abstraction, a lot of nice things happen. Okay. So first of all, this probabilistic abstraction is quadratic in the size of the DNN output, but it's completely independent of the number of DNN parameters. It's independent of the camera, the environment, and so on. Okay. So this is a much simpler object. So if we go back to this figure, the probabilistic abstraction has replaced both these boxes, and this abstraction is basically the simple description of what's going on with those two boxes. And we can plug this abstraction into our system, and now our system becomes analyzable using existing formal methods techniques. Okay, so once we plug this probabilistic abstraction into this model of a taxi net system, the whole system becomes can be thought of as a discrete time Markov chain. So this is like a formal computational model. But again, the details are not important of what is a DTMC, but the main point is there exist tools that can analyze, given a DTMC and given some kind of a safety specification for a DTMC, there already exist tools. These are called probabilistic model checking tools that can tell us whether our system is ever going to violate, or like what is the probability that our system is going to violate our properties. Okay. And this becomes possible because of our abstraction. So you know, if you try to model the original system as a DTMC, this would be an extremely complicated system, and existing tools won't be able to scale to this super complex system, even if you were able to model the environment and so on. Okay. So our probabilistic abstraction basically enables us to now use off-the-shelf analysis tools or formal methods tools to analyze the system. So this is again a good point to maybe stop and check if there are any questions. If not, I'll move on to describing some more things about this case study.
We don't have any questions in the chat yet, Ravi.
No worries. Okay, so let me continue then. So I gave now like an overview of how we might abstract parts of the system so that we can analyze the system. Now we want to go one step further. Okay, we want to further ask how can we make the system even safer. So let's say I analyze the system. I am able to establish some level of safety for the system. The next question is how do we make the system even safer? Okay, and an observation here is over the past few years, several techniques have been developed for analysis of neural networks in isolation. So some of the examples here are there are a plethora of techniques now for certifying what is called the local robustness of neural networks. Okay, basically checking that neural networks are robust to small perturbations. So there are a number of tools that can do this. There are techniques for checking when an input is out of distribution. Okay, so again, lots of tools for doing that. So the question that we are asking here is, how can we leverage these neural network specific analysis, okay, to improve the safety of our overall system? Okay, can we leverage these existing techniques to help improve the safety of the overall system? And the idea here is to use these techniques in what are called runtime guards. Okay, so let me tell you what I mean by runtime guards. So the basic idea is a runtime guard is something that's going to be used at runtime or inference time. Okay, So again, this is the same picture that I had before, but now we have introduced this runtime guard. So before an image is passed to the neural network, it is passed through the runtime guard. And on inputs where the runtime check passes, we expect the neural network to be more trustworthy and more accurate, and we just pass that image directly to the neural network for processing. But if this runtime check, for instance, fails, let's say it fails consecutively a certain number of times, that's an indication that perhaps this kind of this image is shouldn't be processed by the network, and in that case, we should perform some fail-safe action. Okay, so in the example of this taxinet system, let's say our runtime check fails. So the runtime check, for instance, could be I'll give an example of a specific runtime check in a couple of slides, but say the runtime check is checking if the neural network is robust on that particular image, and this runtime check fails. That's a sign that maybe the network is going to make a mistake on that image. And if this keeps happening consecutively a certain number of times, then it's perhaps safer for this automated system to stop taking actions and instead to hand over control to the human pilot. Okay, so to perform what is called a fail-safe action. So that's the role of this runtime check. And basically, we can incorporate this runtime check both in our system design, and we can also analyze the system in much the same way that I described in the previous few slides to check how does adding this runtime guard help improve the safety of the system. Okay. All right, so that was some of the formal theoretical background and like our approach for solving this problem. Now I'm going to describe some experiments that we did. Okay, so basically all our experiments were again in this context of the taxinet system, but we considered two variants of the system. So variant M1 is the one which doesn't have any runtime guard, and variant M2 is one with a runtime guard. Okay. And the runtime guards that we use are in particular rules of the form pre implies post. So pre is a precondition and post is a post condition, which tries to characterize inputs where the neural network is likely to mispredict. Okay, so this pre is a condition, it's a logical constraint over the intermediate neurons of the neural network, and the post is a condition or a logical constraint on the output of the neural network. Okay. And we say that an input passes the runtime guard if it does not satisfy pre, because basically the way to read this pre implies post is if on an input the precondition is satisfied, then the neural network is likely to make a mistake on that input. So we say the runtime guard passes if on an input if the input doesn't satisfy the precondition. And both these variants M1 and M2, we are going to assume they have the same controller and airplane dynamics. Okay. So here are some more details of this pre implies post, the runtime guards. Okay. So this is an example of the kind of rule that we might have. So the way to read this is so N indicates neurons, and the 1 is saying this is the neuron in the first layer, and 85 is saying this is the 85th neuron in that layer. Okay, so basically this is the pre, as I was saying, is some condition over the intermediate neuron values. Okay, and if an input once the network has processed it satisfies this precondition, then the post condition here says that the network is likely to make a mistake. So the gap between the ground truth CTE value and the true CTE value is going to be large, or the gap between the ground truth HE value and the true HE value is going to be large. Okay, so this is just repeating what I said on the previous slide. An important point is we can evaluate these kinds of runtime checks quite efficiently during the forward pass of the neural network, so this doesn't impose too much of an overhead. All right, so one final thing before I show you the results is again a reminder of the safety specifications that we are trying to check for the system. So the first two specifications we already saw earlier. First specification says that the probability that the plane goes up the runway should be bounded. Second specification says the probability that the plane turns more than a certain degree should be bounded. The third specification is new. So this is basically saying that the probability that the system reaches the abort state, which basically means that the runtime guard fails, should be bounded. So here v equal to 0 means the system reached the abort state, and I equal to 1 means that basically the runtime check failed consecutively m times, right? So this is sorry, v equal to 0 indicates that the runtime check failed, and I equal to m says that it failed consecutively m times. So basically, if both these conditions hold true, then the system goes to the abort state. And we would like to check how frequently the system goes to the abort state, because that is not a good thing, right? If very frequently the human pilot has to take over control, then the automated system is not doing its job.
So, hey, Ravi, I had a quick
Yes.
question for property
Yes.
one.
Yes.
Is property one always, in this case here, the width of the runway, or is this also the length of the runway as well?
No, so in this case, it is just the width of the runway. We're
That's
just
what I thought. Okay.
yeah, just ensuring that the plane doesn't go off the edges. Right?
Okay, got it. Okay,
yeah.
thank you.
The length comes in terms of the number of time steps. So okay, let me go to the next slide, and this will I'll call this out.
Okay.
So that was a good question, Amit. And basically, we now analyze our system with respect to these three properties. And let me tell you what these plots are showing. Okay. So on the x-axis is the number of time steps that we consider for our analysis. And this is where the length of the runway comes in. So we're trying to prove for how many steps is the system behaving safely. Okay. The y-axis is the probability of failure, or the probability of violating one of these properties that we stated. So ideally, we want the value on the y-axis to be as small as possible. So let's read these graphs. Okay. So the first, well, okay, one thing I should point out is the green line is the line for the system M1 without the runtime guards, and the blue line is the line for the system with runtime guards. So the first thing that we notice is as the number of time steps increases, the probability of failure increases. And this is not too surprising. So there is always a small probability of failure at every time step. And if the system is operating for longer durations, this probability of failure keeps accumulating. Okay. The more interesting observation here is the system with the runtime guard, which is this blue line, okay, has a lower probability of failure than the system without the runtime guard. So this is something that we wanted, and these experiments show that this is actually what happens in this case. And this leads to like a general takeaway message that I believe quite strongly in, which is for various kinds of autonomous systems that we are building today, runtime monitoring is an essential component for ensuring or helping improve the safety of these systems. And these kinds of experiments kind of support that perspective. The third plot is for property 3. So remember, this was trying to check how frequently the system goes into this abort state. And at least for this simple system and our case study, we see that the probability of going into the abort state is quite tiny. Like it's almost negligible, which is again a good thing. So all of these results were calculated using a probabilistic model checking tool called Prism. If you're interested, I can share the link to this tool. You can also Google for it. And we were able to do this analysis because we replaced the environment and the perception components of the system with our probabilistic abstraction. And all of that made it possible to run these analyses very quickly, right? So I ran them on my MacBook, and they could run within like 0.1 seconds. Of course, the case study here considers a simple system. So if you move to more complex systems, these analysis times are going to increase. But the important point here is without this abstraction that I described, it would not even be possible to analyze a simple system. So that's the key point. So let me quickly go through my next two slides, and then I'll conclude. So one sort of point to convey here is when we were building our probabilistic abstraction, we were estimating the probabilities for these transitions, right? We were estimating the probability that given some true state of the system, the estimated state of the system would be something like we saw the calculation that given HE, the true HE value is 0, what is the probability that the estimated HE value is 1? Okay, so we were estimating these probabilities. But these estimates were calculated using data. So these are really point estimates. And whenever you calculate point estimates, there is a chance that you make an error in your estimation. So that risk also holds true for the estimates that we calculated. So these point estimates basically lack statistical guarantees, and they can be off from the true value of that probability by an arbitrary amount. Okay, so to address this challenge, basically what you can do is you can calculate confidence intervals instead of just calculating point estimates for these transition probabilities in our probabilistic abstraction. We can calculate transition intervals. We can calculate confidence intervals for both the transition probabilities, and then we can also calculate a confidence interval for the probability that the safety properties that we care about are satisfied. Okay, and we are able to do this using some existing tools. There's a tool called FACT, and basically this tool can, given DTMC and a property, a PCTL property, it can, and given basically confidence or confidence intervals or each of the transition probabilities in the DTMC, this tool can do the right thing and calculate confidence intervals for the probability that our safety properties are going to be satisfied. Okay. So just to convey this more visually, basically, again, we have the same properties, property 1, 2, and 3, and here we consider some fixed number of time steps. So I believe this is for 3 time steps. So when n equal to 3, remember the x-axis on the previous plots was the number of time steps increasing, where n was the number of time steps. So here n is equal to 3, and basically what this is showing is the probability of these properties not holding. So for instance, if we want a confidence level of 0.95, this is saying showing sort of the interval, the confidence interval. So if I read this right, it says like the probability that the first property is not going to be satisfied, the probability that the plane is going to go off the runway is somewhere between 0.05 and 0.03 for system M1, right? So that's how you might you can read these graphs. So now instead of point estimates, as we had earlier, we have these confidence intervals. But this now gives us some more confidence in our results, because even if our estimates are not perfect, we can still say with certain confidence that what is the probability that the system is going to be safe by looking at these intervals. Okay, so I'll conclude here, and I just want to go over some takeaways from what I talked about. So one sort of, well, the first thing I mentioned was we want to do formal analysis of these kinds of autonomous systems which are using neural networks for perception, but this is very complex because neural networks are complex, modeling the environment is complex. So the first thing that I presented was we can basically develop these probabilistic abstractions, and they can make our analysis feasible. Okay. Sort of an interesting aspect of this probabilistic abstraction is we constructed it using confusion matrices. And confusion matrices are something that are often calculated anyway when you build a classifier. So the sort of neat thing here is you can use this testing artifact, which people typically construct when using a classifier. And now we can also leverage this for doing some more formal system level analysis. This abstraction that I described actually enables compositional system development and reasoning. Because, for instance, you can abstract away the environment and the perception DNN individually from the rest of the system. So it sort of brings in some compositionality into the reasoning process for the system. And I in this talk, I only presented an average case abstraction, right? We built this abstraction using data, but actually you can also construct a best case abstraction. So for instance, you can assume that your neural network is always going to be perfect. And assuming this perfect perception, then you can analyze the rest of the system and see how the system behaves. So that would be a best case analysis. You could also do a worst case analysis. So basically you can ask, what is the maximum level of error that I can tolerate in my perception such that the rest of the system can still behave safely? Okay, so you can do various kinds of analysis once you start abstracting these parts of the system. Okay, and two takeaways about these runtime guards. So one important point is on inputs that pass these kinds of runtime checks that I mentioned, neural networks typically are more accurate. Like this is basically the whole point of using runtime checking. We want to find inputs where the neural network is likely to make mistakes, and we want to handle those inputs using some fail-safe mechanism. And once we do that, then our experiments also show that these runtime guards can help improve system safety. So that's all I had, and I'll stop here. And I'm open to questions. Thank you.
So thank you, Ravi. If anyone has any questions or additional questions, you could either put them in a Q&A or you can come off mute to ask Ravi. Well, I'll go ahead and kick off, Ravi. One question I had, looking through the paper, I noticed you mentioned there will be some future work. So one of the tasks that you guys had mentioned for future work was you plan to refine the models with finer partitions on the DNNs and validate those through hardware simulations. What type of hardware simulations will you guys be doing in the future, to help validate the model?
Yes. So we haven't started on the simulations yet, but I can tell you sort of the thoughts around that. And there are really two kinds of simulations you can imagine. Okay. So one kind of simulation is not on an actual hardware. Maybe that is what you really want to know about. But one kind of simulation is using simulators. Okay. And in fact, this is frequently, for instance, in the automated driving domain, right? This is very common. You have very mature simulators like Carla, for instance, and you can basically simulate this entire closed loop that I talked about using these simulators and then analyze system behaviors. So that's one style of simulation, and something similar could be done for TaxiNet. And again, there are researchers at Berkeley who have built these kinds of simulators or built sort of the TaxiNet simulation in existing simulators. So that would be one kind of simulation. Actual hardware simulation is harder. Like that basically implies that essentially you want to really simulate this on the actual device. Okay, for this system, simulating it on an actual aircraft may not be possible unless someone like Boeing does it, right? But in a lab, you could do something which was like a toy version of it, right? You could build sort of a toy airplane, for instance, or some other kind of robot, and then you can simulate it. We don't have the hardware like to do the actual simulation for like an actual system. So our capabilities are restricted sort of in our collaboration group to mostly doing software simulations, but yeah, organizations like Boeing and NASA can do more of the actual hardware simulations. I don't know if that answers your question.
Yeah, it does, and leads to a second question. So I know at the beginning of the presentation you outlined, 3 possible use cases, autonomous vehicles, aircraft, and spacecraft on other planets. So I'm curious, what are the other use cases that you guys think TaxiNet will be useful for from a NASA standpoint? Assuming we don't have runaways on Mars and on the Moon quite yet.
Yeah. So well, TaxiNet really is, I would say it's not necessarily sort of system that, so at least I am not aware of something like Taxinet being used, say, on like a rover. Okay.
Okay.
You should. I really think of Taxinet as really like a simple case study that we use to build up our techniques, right? So yes, I can imagine. And again, I am at CMU. I'm not at NASA, so I don't know
Right.
NASA's internal thoughts, but I can imagine um, some kind of autonomous system, right, on a rover. And I can also imagine that you would want to do some safety assurance before you deploy this kind of an autonomous system on an very expensive thing that you're launching, and that's supposed to work on another planet. Like NASA is big on assurance of its systems. Okay.
Right.
So this exercise was essentially intended for thinking about when you have more complex systems, how can you go about analyzing them, right? And Taxinet really is, to be honest, a fairly simple system. But the thing is, even for this simple system, you already start seeing what are the challenges, right? Uh, so sort of okay. For instance, let's say the environment modeling. Okay. One simple thing about Taxinet, although I said environment modeling is really hard, in Taxinet, the environment doesn't have other agents, right? There essentially are no other humans or other cars or whatever moving around in the environment. So we don't really need to worry about that. But if you start thinking about more realistic systems or more complex systems, Taxinet is also a realistic system. But if you start thinking about more complex systems, such as, say, an autonomous driving vehicle, then you also need to think about how the agents in the environment are behaving. Okay. So the environment modeling becomes even more complex than what I already described in this talk. So yeah, Taxinet is really sort of a simple system which already points out the various complexities that come into the picture once you want to start doing formal sort of safety analysis.
Okay.
Yeah.
Makes sense.
Yeah.
Benedict, did you have any additional? Oh, okay. We have a question from Taha. Taha, do you want to go ahead and go off mute and answer your extra question?
Yeah, sure. Hi, Ravi.
Hi.
I have this question: how effective is this in real world? Like after an analysis, you make a model, and
Yes.
how effective this can be in real world?
Yes. So that's a great question. And again, there are many sort of aspects to it. So the first aspect is, so let's just say we are talking about this Taxinet system and we do this analysis. So your basic question is, you have done this analysis, let's say in simulation, how effective is it going to be in practice, right? And that's, I think, that is always a concern, especially when you're doing things in simulation. There is a gap between what you're simulating and what's happening in practice. And what you try and do to the best of your capabilities is to model reality as faithfully as you can in simulation. But there's always going to be some gaps. And I think, one has to, as a system builder, designer, someone who's doing assurance, you have to sort of accept that there is going to be some gap between what I do in my analysis in simulation versus what's going to happen in practice. And that's why this is not the only thing to do, right? Let's say if you were a builder of this kind of a system, you would want to do this analysis when you're designing the system, once you've designed the system. And let's say this analysis says, yes, thumbs up, things seem to be working reasonably well. Then it doesn't mean that you just deploy the system in, say, actual production. You still have to do testing of the system on ground, right? But this is one of the steps in your development process. So if you can't even give some guarantees about safe behavior, say in this modeled world, then there is little hope of having safety in the actual world. So I think you raise a very valid point. Like, can these kinds of results be directly transferred to the real world? The answer is no. But they give you more confidence that when you do this in the actual world, things are probably going to behave reasonably okay. And if they don't, then you can ask, where did my assumptions break? Because you made some assumptions during your analysis in the simulated world, and you can rectify those assumptions, right? You can make some of the changes that the real world is saying you need to make in your simulation or in your assumptions, and then rerun your analysis. So you should really think of this as like a step in the development process, as an important step in the development process.
So every time you face a new scenario in real world, you're thinking in a way you consider new, like you adapt the model to that, and then next phase you add that to the test.
Yes, if you think of it that, so ideally you want to model, say, as many of the real world scenarios that you can think about during your design and analysis phase. Okay, but you might miss out on some scenarios, right? Like that's the challenge with these open world autonomous systems. You don't know all the scenarios that your system is going to encounter. And in that case, yes, you maybe start testing the system, and then you encounter things that you hadn't thought about, and then you bring them back into your design and analysis and run the analysis again. So that's exactly, you're exactly right.
Okay, that is all the questions that we had come through in the chat, Ravi. So I think we are at our hour. So we do appreciate you joining today. This was actually an extremely interesting session. And I'm going to go ahead and kick to Benedict to close us out for today.
Okay. Yeah. So that was actually a very, very interesting session. I didn't really have the time to read the paper that well. So I just skimmed through the paper and then just got a few tidbits from it. But in just 1 hour, you already explained the majority of what I need to know from the paper. So I really appreciate that. And I think I speak for everyone here when I say that the topic we discussed today is something new that we might be excited to look deeper into. So yes, you were mentioning building miniature airplanes for testing and then generating data and all of that. And I was thinking, okay, that's something we could do. But then I thought about it and I realized it's kind of like building a pilot chemical plant where you build it at a small scale and then.
Okay, I think we might have lost Benedict's connection, but again, thank you, Ravi, for your time today, and thanks to everyone for attending today. And this presentation will be available on YouTube within about 48 hours or so. So we'll send out a notice to everyone to let you know when it's available, and we'll send a notice to you as well, Ravi.
Yes, so I just wanted to say thank you so much for having me, and yes, if anyone has any follow-up questions, feel free to reach out to me. I'm happy to discuss, answer your questions. So yeah, feel free to do that. And thank you very much for inviting me.
Okay, sounds good, and good luck with the new semester at Colorado State.
Thank you so much, Amit. Thank you.
Okay, thank you, everyone.